Welcome to the motion section of our review. The four equations will be provided for you on the test. The trick to finding which equation to use, though, is to use very step-by-step method here would really help. And the first step is to circle every variable in the problem and see what variable it is. Is it d, t, v, or a? So for example here, we've got 4 meters per second, and we've got 1 second. So 1 second is, of course, a time. 4 meters per second is a velocity. I know that from the question or from the fact that velocity is always in meters per second, or kilometers per hour, or miles per hour, which is the one you're probably most familiar with. That's a velocity, right? Miles per hour. So this must be a velocity. And then we go, what are we looking for? What distance will it travel? D. So v, d, and t. We need to find an equation that has d, v, and t in it and solves for d. D equals vt. What do you know? So now we can go in. D equals vt. It always helps to write the equation first. And then we can do another equal sign equals, and we can just plug in our numbers. If we start with this, we don't have to do very much thinking for the rest of the problem. 4 times the t, 1 equals 4 overall. But we're not quite done because we have to have units in our answer. Units for distance is meters or kilometers or miles. So in this case, because it's meters per second, the distance is in meters. All right, so for this one, it's kind of a trick question. You would go through using our good strategies, right? We're going to circle 7 meters per second. We're going to say, okay, that's a v. Traveling in 5 seconds, that's a t. And we're looking for speed, which is another v. Awfully awkward. We don't have a d to go make our equation happen. And we don't have an a to make one of these equations happen. Well, we have to fundamentally think of what does constant velocity mean. It means that the velocity is not changing. So it's 7 meters per second. After 1 second, 7 meters per second. 2 seconds, 7 meters per second. 5 seconds, 7 meters per second. There's no equation for that one. All right, so for 17, we've got this constant acceleration of 3 meters per second squared. This squared is always what accelerations look like. Accelerations always have a meters per second squared, or kilometers per hour squared. And this is because it's 3 meters per second, which is the same as 3 meters per second squared. And it's per second because acceleration is the change in velocity. So every second, it's changing 3 meters per second in velocity. So after 3 seconds, it would be going 3, 6, 9 meters per second. But that's not what this question is asking. So this is an acceleration. Acceleration, right, and a squared. Those both tell us that this is an acceleration. Travel in 8 seconds is a t. And then what distance is a d? So we've got a, d, and t. Which equation are we going to use? Well, let's look. Okay, this one has VA and T, this one has D and T, but it doesn't have A. A, D, and T. D equals 1/2 AT squared. So if you start here, it's so easy to just plug it in. 1/2 times A is 3 times T is 8 squared. I'm sorry I wrote this here, it kind of got in the way. 1/2 times 3 times 8 squared. If you set this up this far, you'll get most of the credit even if you mess up the math. But the math here is we have to square the 8 first. So I'm going to jump all the way over here. 1/2 times 3 times 8 squared, which is 64. And then we get 96. And then we have to decide on the units. Distance is measured in meters. Also, meters per second squared, there's the meters. All right, last problem. Object is moving at constant acceleration of 10 meters per second squared. Again, it's got to be an A. It's set acceleration and meters per second squared acceleration. Velocity in 2 seconds, t. So a, v, and t. Which equation? V equals at. Equals, and then we just plug it in. 10 times 2 equals 20. And what's our units for velocity? Meters per second, or kilometers per hour, or miles per hour. Meters per second squared, so meters per second. All right, so what does the slope of a distance versus time graph represent? Please do not miss this on the exam. We will be so upset. What does the slope of a distance versus time graph represent? The velocity. Every time. And the reason is, when we take a distance versus time graph, if we're taking the slope of a line, it's rise over run, and the rise is distance, which is the same as distance over time. What do you know? What is distance over time? The velocity. That's why our units are in meters per second, distance per time. It all connects. And the slope of a velocity versus time graph tells us the acceleration. I don't expect you to know that as well, and we're not going to use that information, but it goes another level up. The slope of velocity versus time graph tells us the acceleration, which is why we never have a curved velocity versus time graph. It's because we're always dealing with constant accelerations, which is not the same as constant speed. So constant speed means there is no acceleration, right? So for these 5, these went pretty well, so I'm going to go through this kind of quickly. This has a negative slope. And what does slope represent in distance versus time? Velocity. So if it has a negative slope, it has a negative velocity. When do we have negative velocities? When it's backwards. This has a positive slope. And these are both lines, so their slope is not changing, so their velocity is not changing. That means it's constant. Constant velocity forwards. This one does have a curve. The velocity is changing. Is it increasing or decreasing? We're going to look at the slope. Slope is here, and then by the end, it's here. It's getting steeper. It's getting a higher slope, which means it's getting a higher velocity. Higher velocity means it must be speeding up. This has a velocity slightly above 0 that is not changing as time goes on. It's constant, right? Because now we're in velocity versus time. So this is constant velocity, and it's positive, so it's forward. If the line were down here, it would be backwards because it would be negative velocity. And then we've got velocity versus time, and it's going from a velocity to almost 0 velocity. The velocity is decreasing as time goes on. This is slowing down. So then when we draw these, we're really just drawing the situation. And these went pretty well when I was reviewing this. So constant velocity forward, it's got to be a straight line. You draw like this, or like this, or like this. Those are all good enough, right? Same thing down here when we do velocity versus time. It's constant, so we need flat lines, but we can put it anywhere as long as it's above 0. If it was below 0, that would be our constant velocity backwards. These are constant velocity backwards, and that would have a negative slope, like this, or like this, or like this. Any of those work, because as long as it's a straight line. Acceleration speeding up. Now, we've seen this one up here, acceleration speeding up, so I'm going to show another version of acceleration speeding up, would be like this. Now, this one is good too, but this one I wanted to show you because this also has an increasing slope. It's just increasing negatively. It starts off at almost 0, very low slope, and it gets more and more negative. That's speeding up. And velocity, in this case, if I was graphing this exact same one, I'd be in the negative side with an increasing velocity. Going from 0 to 2, negative 2, right? Also works 0 to 2. Those are both correct for acceleration speeding up. This one is just the graph of this one, going negatively. Then slowing down, again, this could be positive or negative. I'll just do the simpler one. We're going to go start with a high velocity and be slowing down, flattening out. Steep at first, getting flatter. And start at a high velocity, slowing down. Slowing down, which if we were going to go negative, this would work. Negative 2 to 0, because that's getting slower. And then at rest is any flat line here in distance versus time, and the flat line needs to be along 0 in velocity versus time. So that's motion.